Okay, let's jump right into today's explainer. We're going to unpack one of the most accessible yet absolutely fascinating scientific experiments known to humanity, observing the phases of the moon. You know, in physics, we so often think of experiments happening in a split second, right? Like a dropping ball or a laser beam instantly passing through a prism. But some experiments take hours, days, weeks, or even years for meaningful results to emerge. Today, we're focusing on a data collection journey that unfolds over several weeks, literally right above our heads. Let's get started.
So to really appreciate our objective here, we have to look back at history for just a second. For thousands of years, cultures all over the globe have used observations of the sun and the moon to build calendars and structure their years. But there's this incredible discrepancy between the two measurements. Our modern solar calendar is based on a year of 365 days, which is roughly the time it takes for the Earth to orbit the sun once. The lunar calendar year, however, is significantly shorter. It relies on 12 repeats of the 29.5 days it takes for the moon to complete its orbit around the Earth. If you do the math on that, 12 times 29.5 only gives you 354 days. That means we have an 11-day difference every single year.
Now, what's really fascinating about this is how that 29.5-day cycle actually changes the real-world dates of global festivals. Since the lunar year is about 11 days shorter than the solar year, traditions that are tied to the lunar calendar don't just stay fixed on our modern 365-day wall calendars. This is exactly why the dates for Ramadan, Chinese New Year, and Easter shift around annually. It's just a beautiful example of how celestial mechanics, the literal physics of space, directly impact human culture and our daily lives.
Section 1. Tracking the lunar phases.
So how do we actually track this celestial cycle ourselves? Well, the best part about this experiment is that there are practically zero safety risks, and you only need the most basic apparatus: a clock, a compass, and your own eyes. Here's the practical methodology for our data collection. Step 1. Find out what time the moon rises and sets. Step 2. Look at the moon and identify its phase. Step 3. Record your results and make a quick sketch of its appearance. And finally, Step 4, repeat your readings about every 3 days over the course of a month. You'll also want to record the direction on your compass where the moon is rising and setting. It's really all about consistent observation over time.
And right here is the exact framework we need to use. Structuring your data is absolutely critical in any physics experiment. By keeping a neat table to track the date, the phase, your sketch, and the precise times of the rise and set, you're transforming casual stargazing into rigorous scientific data collection. As you fill this out over several weeks, you'll see a very clear pattern begin to emerge.
Let's just make sure we're entirely clear on our terminology before we go out into the field. A phase is simply the identifiable appearance of the illuminated portion of the moon. Think of the new moon, the crescent moon, the half moon, and the full moon. Now, catching the moon rise can actually be pretty tricky if you don't know when to look. A quick pro tip is to use your local newspaper or just hop on the internet and search for local moonrise times. That way you know exactly when to start your observations. Before we move on, I want to highlight another fantastic pro tip from our source material that honestly surprises a lot of people. A full moon is visible only between sunset and sunrise. It is an exclusively nighttime phenomenon. However, the other phases, like the crescent or the half moon, can actually be seen during daylight hours if you know where to look. So definitely keep your eyes on the sky even during the day as you run this month-long experiment.
Section 2. Evaluating the moon data. Let's dig into what it all means.
Okay, so you've spent a month collecting your data, identifying phases, and sketching shapes. Now it's time to ask the big analytical questions. Really think about this for a second. Where does the visible light come from? We see the moon glowing brightly in the dark night sky, but the moon itself is just a massive rock, right? It doesn't generate its own light like a star.
Which immediately brings us to this next vital question. If the light is hitting the moon, why isn't the full disk of the moon always visible to us? Why do we see a crescent one week, a half moon the next, and sometimes practically no moon at all during a new moon? Think about the spatial relationship of the celestial bodies involved here.
Well, the crucial point here is that the sun is our powerhouse. It provides all the light that reflects off the lunar surface. The sun is actually lighting up exactly half of the moon at all times. But because the moon is constantly moving in its 29.5-day orbit around us, Earth's position relative to that illuminated half is always changing. And that angle is what decides what fraction of the light we actually get to see from down here.
Section 3. The Earth-Moon-Sun System.
To truly grasp this, we've got to zoom out to a macro perspective and map out our observations from space. Creating a visual model is basically a superpower in physics.
First, picture drawing the Earth right in the center. Then, draw a circle around it, representing the Moon's orbit, placing the Moon at different positions on that path. Next, show parallel rays of light coming from the Sun way off to the side, hitting both the Earth and the Moon. Finally, shade in the portions of the Moon that would appear dark from our perspective on Earth. When you draw this top-down view, the geometry of the phases suddenly makes perfect, intuitive sense.
All right, let's put that mental model to the test with an evaluation question. Based on the map we just built in our minds, does a full moon occur when the Moon is nearer to the Sun than the Earth, or when it is further from the Sun than the Earth? And the answer is, the full moon happens when it is further from the Sun than the Earth. Just think about the alignment for a second. For us to see the entire illuminated face of the Moon, the Earth has to sit exactly between the Sun and the Moon. The sunlight streams past us and directly lights up the side of the Moon facing us. When the Moon is nearer to the Sun than the Earth, the illuminated side is facing entirely away from us, which gives us a dark, new moon.
As we wrap up this explainer, I want to leave you with a going further challenge directly from our source material. We know it takes about 29.5 days to complete a cycle, and we know the Sun provides the light. But why does the Moon rise at a slightly different time each day? Ponder that. Think about the continuous, simultaneous rotations and orbits happening right now, the Earth spinning on its axis while the Moon slowly inches along its orbital path. It is a brilliant puzzle of motion. Keep observing the skies, keep asking questions, and I'll see you in the next explainer.